Alright, so to help you out a little bit, I thought that I would go through the thermal energy notes that are included in your packet. This is the third concept. This is actually a little bit of new information that we're going to start to cover today. And since we have not formally gone over this material in class, and since I'm not going to be able to see you for a little while, I figured that I would make a video where I could go through this information and help you out a little bit. And I could also maybe elaborate a little bit more than what is on your notes alone. So as we go through this, I highly encourage you to have out your packet and have the thermal energy notes out in front of you. Also maybe have a writing utensil, and feel free to write down any extra notes that you want to add to your notes itself. You could have out a scrap piece of paper as well, whatever works for you. Just not a bad idea to maybe write down some of the thoughts. And again, you don't have to watch this whole video, but it is a good thing to maybe kind of use this as a resource. You could scrub through the video a little bit, find the specific parts that you're having a little bit of difficulty with, and kind of look and use this video to help you out a bit. So we're going to talk about thermal energy today. We've talked about kinetic and potential energy in our first concept. We even actually calculated the specific values for kinetic and potential energy given a situation. And then in the second concept, we talked about energy transfers and the different types of energies that are there. We talked about, things like sound or acoustic energy. We talked about radiant or light energy. We talked a little bit about thermal energy. We talked about electrical energy and things like this. We talked a little bit about nuclear as well, and also electromagnetic energy. So we're going to talk about thermal energy specifically today. So without further ado, let's just jump right into it. And we'll just provide the definition for thermal energy, and it might look a little familiar to you. The definition of thermal energy is the sum of kinetic and potential energy of the particles in an object. So basically you're just adding up all of the kinetic and potential energy of the particles. And remember, particles are just atoms or molecules, so things that we really can't see, but we're just adding up that energy of those particles. And remember, we talked about it last semester, even though you really can't see this, all objects are kind of moving. They have a little bit of kinetic energy at all times. Especially solids, you might look at a tabletop and think, wow, that solid tabletop looks pretty inactive. It's not really moving, but technically on an atomic level, those atoms are moving ever so slightly. We just can't perceive that motion. So those surfaces have a little bit of kinetic energy. Some things to be aware of as we go forward here is that thermal energy is going to increase as mass increases. So thermal energy generally increases as mass increases. There is a direct relationship. The reason that is, if we look back to the definition, it's the sum of kinetic and potential energy of the particles in an object. So again, the key word there, particles. So if you increase mass, you basically are increasing the amount of particles in that object. So it makes sense that if you increase particles, you increase the amount of energy that they might have, and therefore the thermal energy is also going to increase. Another way of thinking about this is that the sun, which is the most massive object in our solar system, well, the sun obviously radiates a lot of thermal energy. Because the sun has a lot of mass, it is literally made of so much matter that it is just going to radiate all this thermal energy because it really has a lot of kinetic and potential energy of all the atoms that comprise the sun. Another thing to be aware of is that thermal energy is going to increase as temperature increases. So that's another direct relationship. And it's, for the most part, pretty intuitive. It makes sense that as thermal energy or heat energy increases, you are going to see a rise in temperature. And speaking of temperature, I want to provide the formal definition for temperature, which is very similar to thermal energy, and we've talked about it in the past. But just remember that thermal energy is really just a measurement of the average kinetic energies of particles in an object. And the higher the temperature, the faster those particles are going to be moving. Just something to be aware of as well. So the higher the temperature, the faster those particles are moving. Same thing in reverse. The lower the temperature, the slower those particles will be moving. And that is our definition of temperature. So moving on here, I got a little bit of a question for you. How do you know if someone has been sitting in your chair? So let's say bell rings for first period, you are in my class second period, you come in to sit down in your chair. How are you going to know that someone was occupying that seat in the first period? Well, if you're thinking about it, your answer is probably going to be it's a little warm, right? Now, why is that chair going to be warm? The chair is going to be warm because thermal energy kind of follows this general rule that it is going to flow from higher temperature objects to lower temperature objects. So if you think of the human body, we have an internal temperature of about 98.6 degrees Fahrenheit. And then it kind of varies a little bit what your skin temperature would be. It's a little less than that, maybe around 80 degrees Fahrenheit. So obviously, you are typically going to be a little bit of a hotter object compared to that chair that is just sitting in room temperature, so around 72 degrees Fahrenheit. So you, the higher temperature object, are going to transfer energy, your thermal energy, to the lower temperature object, which is that chair. So realistically, that's just highlighting there that we humans, we transfer our energy all the time, and we also have energy transferred to us from outside factors, maybe even like the sun transferring thermal energy. So realistically, just remember that thermal energy is flowing from higher temperature objects to lower temperature objects. That leads us into our next definition, which is heat. And you'll notice that I have a Q in parentheses next to heat. That is because in calculations that we're going to do later, we do represent heat as a Q, uppercase Q. And heat is really just the transfer of energy from one object to another. That's really what we can just measure heat as. And since it is energy, it is going to be measured in the same unit that we've been using throughout this unit, and that is going to be joules. Remember, we measure all of our energy in joules, whether it be kinetic, potential, whatever it may be, it will be measured in joules for this unit. So we talked a little bit about energy, thermal energy there, gave a little bit of background behind it and the definition. Now we're going to talk about how that thermal energy can be transferred. But before we do that necessarily, we need to realize that there's a little bit of a common misconception. So people, when they think of temperature specifically, they think, oh, it's something's hot or cold. You know, it's hot outside today or it's cold outside. But realistically, there is no such thing as cold. The reason something feels cold, or it might feel cold outside, is that it is just simply an absence of heat. You know, the reason you might pick up, in this example here with the kid here drinking a bottle of water, it might feel cold because there's an absence of heat. You know, that ice cube is a lot colder than the surrounding environment. So the example to explain it even further is that basically what's happening here is that there's a little bit of an energy transfer going on. So the water bottle here has ice cubes in it, so that is dramatically cooling the temperature of, or lowering the temperature of the bottle compared to the outside environment, especially in relationship to the hand of the individual that's holding the water. So essentially what's happening here is that you're having a little bit of an energy transfer. When you're holding the bottle in your hand, the thermal energy is actually escaping. It's being transferred from your hand to the water bottle. It's almost like the water bottle is pulling heat away from your hand. That's why the hand starts to feel cold, and that's why the water bottle inevitably will heat up a little bit because it's pulling some of that thermal energy out of your hand. There's an example or a problem like this on your first assignment for thermal energy. I believe it's your third assignment overall in the packet, but it is basically thermal energy calculations. And one of the questions at the beginning is going to ask you essentially like a scenario, I believe, where it's a cold winter day and you are standing at a bus stop and you get on the bus, and to warm up your hands, which have gotten very cold in the surrounding atmosphere, you kind of stick them underneath your legs to kind of help warm them up, but then your legs start to feel a little cold. So really, what is happening there? Why do your legs start to feel cold? And what I encourage you to do is think about this slide. Think about the energy transfers, the thermal energy transfers that are happening. And last couple things here is that generally when heat flows into an object, the change is going to be, and heat is going to be positive. So the water bottle in this case is having heat flow into it, so it is going to heat up. And the reverse of that is when heat flows out of the object, the change of heat is negative. So the individual's hand here, his hand is going to lose a little bit of heat because it's being transferred to the bottle, so he's going to feel like his hand's a little colder than it might be. So that's transfer of thermal energy. Now we're going to talk about 3 specific ways that thermal energy can be transferred. The very first way, I guarantee you've heard of it last year. In fact, you've probably heard of the first 2 ways last year, but the first way is going to be conduction, and that is the transfer of energy through matter by direct contact of particles. So for instance, if you take a pot of water and you set it on the stovetop, it is going to be in direct contact with that stovetop. The stovetop is going to heat up using whatever method it might use. Could be a gas stove, could be an electric stove. Either way, it's going to heat up and it's going to be in direct contact basically with that pot of water, which is going to transfer thermal energy directly through that pot of water. Now, when you're talking about conduction, key things to be aware of is that solids are going to be the best conductors of heat. They're easily going to be able to transfer heat energy or thermal energy from one object to another. And this is because, if you think about it, solids are made of atoms that are really, really close together. So these particles are already so close together that it's really easy to transfer this energy because they're right next to each other. It's like if you bump into somebody and then they bump into another person in a really crowded place, it's easy to accidentally transfer, your energy. If you accidentally tripped and you bumped into someone, it's going to keep going down the line. The same thing is true with these solid particles because they're already so close to each other. So with conduction, a key there, especially if I ask a question later where I give you a scenario and I want you to identify if it's a thermal energy transfer or what type of thermal energy transfer. Conduction, pay attention to that direct contact there. Things are directly touching each other. The next one, which you also have probably already heard of, is convection, and this is going to be the transfer of energy by movement of heated particles. Convection, you've commonly probably heard of this as in convection currents in the Earth's mantle. So the Earth's mantle, that kind of thick layer of the Earth where essentially you have all this molten magma, molten rock and everything, that is going to be heated up towards the Earth's interior or closer to its core, and then that heated material is going to start to move upward, and it's going to move towards the outer layer of the Earth or the crust, and then it's going to cool down, and then it's going to move back down towards the Earth's interior, and it keeps those convection currents going. Similar to the teapot example that I have here on the slide, where you basically have the tea kettle here, where essentially the hot water is at the bottom of the tea kettle, and that's near the stove, so it's going to get heated up, and then it's going to rise up to where the cold water is at, and then the cold water is going to flow down to where the hot water is at, and basically that's just convection currents happening there. And it's just a transfer of energy by movement of heated particles. There's no real direct contact here, which is a key difference between conduction. And another key difference, it typically only occurs in liquids and gases. It typically only occurs in liquids and gases. That's why you have convection currents in the mantle, which is for the most part a liquid substance. It's kind of not exactly, but similar to a liquid. And then convection currents also occur in the atmosphere. Hot air rises, cold air sinks. That occurs in the atmosphere as well. And then another last thing, just currents move heat from warmer to cooler parts of the substance. Just reiterating there, that's what happens in our atmosphere every single day. And then the third way has to do a little bit with especially the sun, because this does a lot of thermal energy transfer. And the reason the sun can do a lot of thermal energy transfer is it's going to transfer energy through radiation. And this radiation is transfer of energy through specifically electromagnetic waves. We talked about the electromagnetic spectrum a little bit before break, but remember this electromagnetic spectrum is basically these photons or light particles. They can be excited, and by excited I mean they can have different levels of energy. So for instance, the electromagnetic spectrum, where you have these low energy light particles, those are called sometimes radio waves. And then you have these high energy light particles, and those are called either gamma rays or X-rays. It's just a spectrum of basically low energy to high energy. And that is a great way of also transferring thermal energy. So for instance, if you've ever asked yourself a microwave, how does a microwave work? Well, it works by using microwave radiation. That's a type of electromagnetic radiation. And that essentially is transferring energy by exciting those water molecules that are in your food in the microwave. And that's really what's heating it up, is that this microwave radiation is heating up whatever food you might have in the microwave. Generally, it's going to occur fast in gases. It can be absorbed or reflected. That's why our atmosphere absorbs or reflects a lot of thermal energy depending on the circumstances. So for instance, we could absorb some radiation from the sun, but we could also reflect it depending on what the composition of our atmosphere would be. Some gases are better at absorbing and trapping heat. Some gases are better at reflecting heat. But realistically, all you need to know is that they can be absorbed and reflected, and they can travel through space and between molecules, which is interesting, because if they can travel between molecules, you basically have this energy traveling through very, very small spaces. And it's important to know that it can travel through space because obviously we're getting a lot of thermal energy from the sun. The Earth is warmed mostly due to a lot of thermal energy that is transferred to us from our sun. So it's good that these particles can easily flow through space, and this radiation can move through space. So now we've talked about our three ways that energy can be transferred. We have conduction, convection, and radiation. Now we're going to talk a little bit about the materials that can either basically conduct or insulate. So basically, can you easily transfer heat, or could you not easily transfer heat? So some of those materials could be solids, which generally transfer heat very well, or gases, which generally transfer heat not very well. So we have a special name for materials that transfer heat very well, and we call those conductors, and they easily allow heat to flow back and forth. Common examples of this: metals. That's why we use metal pots on the stove. Those are great conductors of heat. They will easily get your water boiling quickly because they can transfer that energy from the stovetop to the water without too much concern. And then skin is also a pretty good conductor as well. And then the reverse of conductors are what we actually call insulators. And these are materials that do not allow heat to flow very easily. Common example I can think of this is essentially if you've ever had coffee in the morning, if you like to drink coffee or even hot chocolate, whatever it may be, and you want to keep it warm, you might put it in a thermos. That's because those thermoses are made of materials that do not allow heat to flow very easily. They're made of materials that's going to trap that heat in and make sure that it doesn't escape. For instance as well, insulators are very good, or insulation is very good in your homes. So for instance, in the wintertime, obviously you want to trap all of that heat inside your home so that it doesn't get very cold inside. So you might use a little bit of insulation or fiberglass insulation to keep the heat inside. And then on the opposite end of that is in the summer, when you're trying to maintain a nice cool temperature in your house, you really want to keep that heat out. So insulators are just great materials that create a nice barrier that does not allow heat to flow very easily. Common examples: air, wood, styrofoam, plastic, fiberglass. Again, that's usually what insulation's made of. Great insulators. Styrofoam makes sense that we make our coffee, those disposable coffee cups are made out of styrofoam because they don't heat up very well. And then moving on to our next topic, which is going to involve a little bit of some calculations, and this is definitely going to be a new concept, and I just want you to bear with me here. It might seem a little scary at first, but I promise you, as we go through this, it'll be okay. And again, like I said, feel free to email me with any of your questions at any time. I included my email in my packet on the very first page, so make sure you email me with questions, because I bet that you're going to have questions specifically about specific heat. And all you really need to know about specific heat is that different objects and different substances are basically going to heat up and cool down at different rates. For instance, if you've ever been to the beach on a hot summer day, like a 90-degree summer day, and you step on the sand could be really hot. In fact, it could almost be unbearable. That's because sand has actually a pretty low specific heat. It really doesn't take much energy, thermal energy, to heat up the sand, because again, the sand is a solid. It is going to be generally a decent conductor of heat, so it is going to heat up much more easily. But on the same summer day, if you walk into the water is going to feel much colder in comparison, because water actually has a higher specific heat. So a way of thinking of specific heat is basically it's just the energy needed to either cool or heat up a substance for the most part. That's kind of a simple definition. The formal definition we're going to give for this class is basically the amount of heat needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius or Kelvin. We're going to use Celsius in this class. Kelvin, that K there, that is just another unit of measurement. It's on the same scale for the most part, but realistically you just need to know that it's the amount of heat needed to raise the temperature of a kilogram of any material by 1 degree Celsius. Specific heat, oddly enough, the name kind of implies it, is going to be specific to different types of materials. So like I said, different materials are going to have different specific heats. And we can measure these specific heats by what's called a calorimeter. And essentially, if you ever ask yourself what a calorie is, a calorie, so how we measure how much energy is in food, is actually the specific heat of water. So the calories that you see on the back of a food label, if something's 500 calories, that's actually just 500 times the specific heat of water, basically. And the specific heat of water is actually about 4,190 joules per kilogram Celsius, which is actually the units for specific heat that we're going to talk about here in a second. But a calorie is actually just the specific heat of water. That's a little fun fact there, if you didn't know that. And we are going to be able to calculate specific heat using the following equation, and that is Q equals mc delta T. That might look a little scary, but we're going to break it down. I promise it's not as bad as you really think, and realistically it's just some multiplication and some subtraction when it all comes down to it. And Q, again, don't forget earlier in the slides, we talked about Q is actually just the change in thermal energy or heat. It is basically just how hot or cold something got. It's the change in thermal energy. And since it's a measurement of energy, or the change in thermal energy, it is going to be measured in joules again. Remember, joules are our units of energy. M is still mass. We measure mass in this class as kilograms. And then C, which is a new variable, C is specific heat. So that is the specific heat in this problem. So mass multiplied by specific heat, and a new unit here. Might not be a bad idea to highlight this, underline it in your notes, write it down, so make sure that you're including this unit when you're calculating specific heat, is that specific heat is measured in joules per kilogram for every degree Celsius. Joules per kilogram for every degree Celsius there. And then lastly, we have delta T. Delta just means a change, so that triangle just means a change. It's a change in temperature. So essentially, you're just going to take TF minus TI. TF is the final temperature. TI is the initial temperature. So basically, the ending temperature minus the starting temperature. And that is how you are going to get your change in temperature there. And again, we're using metric units, so it is going to be measured in degrees Celsius. So I am going to walk you through some other examples in another video. Specifically, I'm going to walk you through the first two problems that are on your assignment for this week for specific heat calculations and thermal energy calculations. I will walk you through that later, but I'll just show you one quick example here, and then we'll wrap it up. So the example that we have here is that a wooden block has a mass of 20 kilograms and a specific heat of 1700 joules per kilogram Celsius. Find the change in thermal energy of the block as it warms from 15 degrees Celsius to 25 degrees Celsius. So we know in this problem we are going to be adding energy, thermal energy, because we are warming up the wooden block. So after you have read the problem, the very first thing you should do in my class, I encourage it every single time, especially because we have quite a few variables here, you need to define what variables you are given. So in this problem, the very first one we're given is we know the mass of the wooden block is going to be 20 kilograms. Now I was generous to you in this problem and I gave you the specific heat of this type of wood, and it is 1700 joules per kilogram Celsius. So make sure you jot that down next. And then the next values are given is we know the block is warming from 15 to 25 degrees Celsius. So if it's going from 15 to 25, that means our initial temperature is going to be 15 degrees Celsius and our final temperature is going to be 25 degrees Celsius. And then lastly, we do not know what Q is. Remember, that's the change in heat, so we will just write it as a question mark. And then, not a bad idea to write the formula that you are going to be using to solve this problem. And then lastly, not a bad idea to also rewrite that delta T can be rewritten as TF minus TI. I believe that is already done for you on your assignment for this week, but just to help you out a little bit, not a bad idea to get in the habit of writing it out as TF minus TI, the final temperature minus the initial. So at this point, we realistically have everything we need. We can just plug it back into the equation. So what we will do is we will just write that Q is going to equal 20 kilograms multiplied by 1700 joules per kilogram Celsius multiplied by 25 minus 15. Now, not a bad idea. I noticed how we put everything in parentheses to kind of represent that it's multiplication, but it's not a bad idea to get in the habit of following order of operations. I would most likely subtract those two values first, the 25 minus the 15. I think that's going to make your life a whole lot easier. So anytime I give you two temperature values, you should subtract those two values first when solving these specific heat calculations. So essentially what we have here is, now I've simplified it a little bit. All I did was 25 minus 15, and that's going to give us a temperature difference of 10 degrees Celsius. And then the last thing you got to do is just plug it into your calculator, and it will just be 20 multiplied by 1700 multiplied by 10, and that should give us about 340,000 joules. Remember, no naked numbers in this class. Don't forget to include your units there, and we are measuring in joules. So that is actually where I'm going to leave it today. If you have any questions, again, feel free to email me. At the email address provided on the very first page of your packet. I will try to get back to you as soon as I can to answer any questions, and be looking for future videos that might be posted. You know, we're trying to do our best here, so I'll keep posting as many videos as I possibly can that I think would help you out. And that's about it for this video. Hope it was helpful. Have a great day.